What specific problem does the RLVR method aim to solve, and how does it seek to address the existing challenges in reasoning tasks?
The RLVR method aims to enhance the reasoning capabilities of large language models, LLMs, by optimizing them through reinforcement learning with verifiable rewards, specifically targeting the challenge of improving performance on complex logical tasks, including mathematics and programming. It seeks to address existing challenges by fine-tuning a pre-trained base model using reinforcement learning, which utilizes simple, automatically computed rewards to guide the model towards higher accuracy in generating correct solutions. However, the method faces the issue of support preservation, where it primarily reweights probability mass within the existing distribution of the base model, often leading to empirical support shrinkage, where RLVR fails to recover correct completions that the base model could access. This conservative optimization results in improved precision at the cost of reduced diversity in the output distribution, highlighting the need for explicit exploration mechanisms to discover novel reasoning patterns. Ultimately, while RLVR enhances pass-at-one accuracy, it may limit the model's ability to explore and generate a broader range of valid solutions, necessitating complementary strategies to foster genuine exploration.
How does the proposed RLVR algorithm work? Illustrate the methodology step by step.
The proposed reinforcement learning with verifiable rewards, RLVR algorithm, operates through a series of structured steps. First, it begins with a pre-trained base model that generates an output distribution, Q, Y, mid X for a given prompt, X. Next, RLVR employs a reward function, Rx, Y, to evaluate the correctness of the generated outputs guiding the learning process. The algorithm then updates the model's distribution, pi_theta Y mid X, using on-policy gradient updates based on the rewards, while maintaining a regularization term to prevent divergence from the base model's distribution, effectively ensuring that the updates are conservative. This is formalized through a variational inference framework, where the optimal policy is derived to maximize expected rewards while minimizing the Kullback-Leibler divergence from the base model. Finally, the algorithm incorporates an exploration mechanism, allowing it to seed probability mass into underrepresented regions of the solution space, which is crucial for overcoming the inherent limitations of the base model's support and enhancing the diversity of outputs.
Can you provide a simple yet illustrative example demonstrating how RLVR operates to modify the probability distribution of tokens across different reasoning tasks?
RLVR modifies the probability distribution of tokens by concentrating probability mass on high-reward completions while often reducing the overall diversity of outputs. For instance, in mathematical reasoning tasks, RLVR may enhance the model's ability to produce correct answers by sharpening the distribution around known high-reward solutions, thus improving pass-at-one accuracy from 48.9% to 65.4%. However, this sharpening effect leads to a decrease in answer-level entropy, indicating that the model converges on fewer distinct solutions. For example, while RLVR might successfully recover a correct answer like 42 for a math problem, it may fail to explore alternative correct answers that the base model could have generated, resulting in empirical support shrinkage. This illustrates how RLVR's optimization process, while effective in improving precision, can limit the exploration of diverse reasoning paths, ultimately confining the model to a narrower set of outputs.
What are the theoretical benefits of leveraging RLVR compared to traditional reinforcement learning methods, and how do these advantages manifest in empirical results?
Theoretical benefits of leveraging reinforcement learning with verifiable rewards, RLVR, compared to traditional reinforcement learning methods include its ability to optimize a pre-trained base model using simple, automatically computed rewards, which enhances precision in output distributions. RLVR is inherently conservative, making minimal updates to the base model's distribution while ensuring improved performance, as evidenced by the consistent gains in pass-at-one accuracy across various benchmarks, increasing from 48 9% to 65.4% for Pro RL. This optimization leads to sharper distributions concentrated on high-reward completions, which is particularly advantageous in tasks requiring precise solutions, such as mathematical reasoning. However, empirical results also reveal a trade-off, as RLVR tends to reduce answer-level entropy, indicating a collapse onto fewer distinct solutions, which can limit exploration of diverse outputs. Overall, while RLVR enhances sampling efficiency and precision, it also highlights the need for explicit exploration mechanisms to maintain a broader solution space.
How was the effectiveness of the RLVR method validated? Discuss the datasets used, the experimental design, and key performance metrics that were assessed.
The effectiveness of the RLVR method was validated through extensive experiments across diverse datasets, specifically categorized into math reasoning tasks and non-math reasoning tasks. The math reasoning benchmarks included Math 500, Minerva, Olympiad Bench, AMY 2024 and AMY 2025, while the non-math tasks encompassed Simple QA, Live Bench, SciBench, and Reasoning Gym, which featured a variety of reasoning questions. The experimental design involved setting different sampling budgets, with K values ranging from 1024 to 16,384 for Reasoning Gym, and a fixed K equals 32 for math reasoning benchmarks, ensuring that any unreachable completions were below a low threshold under the empirical support of the base model. Key performance metrics assessed included pass-at-1 accuracy, which consistently improved from 48.9% to 65.4% for Pro RL, and the analysis of entropy metrics, revealing a systematic reduction in answer-level entropy, indicating a collapse onto fewer distinct solutions. This comprehensive evaluation underscored RLVR's strengths in precision, while highlighting its limitations in maintaining diversity across outputs.
What results were specifically achieved in the empirical evaluation of the RLVR method? Can you quantify the improvements in pass-at-K metrics and discuss the significance of these findings?
In the empirical evaluation of the RLVR method, significant improvements were observed in pass-at-1 accuracy across all benchmarks, with average performance increasing from 48.9% to 65.4% for Pro RL, and from 43.0% to 61.29% for DAPO. However, while RLVR consistently enhances precision at pass-at-1, it also leads to a notable shrinkage in empirical support, where RLVR fails to recover correct completions that were accessible to the base model. For instance, RLVR missed 3 solutions on AMY 2024 and 26 on Olympiad Bench, indicating that despite higher precision, the model's ability to explore diverse solutions diminished. This highlights a critical trade-off. RLVR's optimization improves immediate accuracy but narrows the exploration of potential correct answers, which is particularly significant in tasks requiring diverse reasoning. Overall, these findings underscore RLVR's role as a precision enhancer rather than a broad driver of novel reasoning capabilities, emphasizing the need for mechanisms that promote exploration alongside reward optimization.